right, here we go for another round of Vodcast. So here we go with Newton's third law. This was also in his Principia, his famous work, of which I have a very thick book that has all of it in it, which I still haven't read. But that's besides the point. So Newton's third law, here's the deal. It can be very confusing, and it's sort of separate from the first and second law in a sense, but in a very real physics sense, the first three laws kind of say each other. Let me explain. Newton's third law, okay? First of all, you've got the Latin here, okay? Now, Latin was the way to write scholarly things back in the day. Why? Because it was the smart language, okay? But it's, lexicon 3, that stands for third law. Actione contrarium semper et aquilum esse reactionem. Sive corporum duronium actionis sensu mutuo semper dirigibles. Okay, I don't know. But here's the basic idea. For every action, there is an equal but opposite reaction. You've heard this before, but I don't like the way this is stated, okay? Because it kind of gets confusing, okay? So, what is an action? What's the difference between an action and a reaction? And why are they equal but opposite? Okay, so why is this going on? What's happening? That's the easy way to remember it, but it's not the best way to remember it. Okay, another way to look at it is the Latin. What it really kind of says here is the mutual forces of action and reaction between two bodies are equal, opposite, and collinear. Okay, so the mutual forces of action and reaction between two bodies. So let's do things hit. They're equal, opposite, and that's still confusing. Okay, let me explain it one last way. Okay, if you have object A, okay, let's say it's my fist. Okay, if it exerts on object B, let's say my face, object B will exert a force on object A. Okay, so if my fist punches me in the face, my face also exerts a force on my fist. And that makes sense. There's actually lots of ways in which this makes sense. If you've ever hit a baseball, okay, when you swing and you hit the ball, your bat slows down. Not only did you exert a force on the ball to make the ball's momentum change and the ball's speed and velocity change, but it produced the exact same force on your bat in order to slow it down, okay? Because your bat is more massive, okay, it's not going to slow down as much as the baseball accelerated, okay? So the baseball exerted a force on object B, it slowed down the bat, and the bat exerted a force on object A, which accelerated the ball. So they both accelerated. The ball accelerated in the opposite direction, and so did the bat. It slowed down. It decelerated, if you will. Now, here's a key point here, is that these forces will be of the same type, equal in size. Equal, that's key. Okay? And opposite in direction. So when the baseball comes in, I wish I had a ball here somewhere. But as the baseball comes in and the bat hits it, the bat's exerting a force in that direction, and the ball is exerting a force in its direction of motion. So it slows down the bat accelerates the ball. That's what's happening, okay? There's lots of different ways in which this happens. Now, a simpler way to put this might be that action equals negative reaction. That's probably the easiest way to think about it. Whenever there's an action, there's a reaction, but I still think that action and reaction is kind of confusing. So I want you to think of if object A, whatever object A is, if it pushes with a certain force on object B, well, guess what? Object B pushes back with the exact same force, but in the opposite direction, perfectly in the opposite direction. Let's think of some other ideas. Okay, I said the punch, okay? My hand hits my face and my face hits my hand. They both get a force. If I go and I punch somebody and I miss, what happens if you miss? Well, you sort of totally go way too far and you're off balance and everything because you're expecting to hit and be slowed down. So when you hit, your hand slows down and it accelerates the face of the other person. Don't do that at home. Please do not try that with your brothers and sisters. I don't want to get phone calls. Let's see another one. Oh, sitting in the chair. Okay, gravity is pulling me down, right? So my butt's exerting a force on this chair. And guess what? The chair is exerting a force back up. In fact, we know what that's called. Okay, we know that gravity is pulling down on you, and the normal force is pushing back up on you. That's an action and reaction pair. The action might be me sitting. The reaction is the chair pushing up. The earth and you, in a sense, because you've got the earth and, let's see, you, okay? The earth is pulling on you, but guess what? You are also pulling on the earth. So why doesn't the earth move? Because you have way less mass in the earth. That's why. So, let's see, another one. Oh, if you're shooting a gun, okay? Let me put that up here. If you shoot a gun, okay, let's see if I can draw a gun. Not really a gun person, okay? So there's a gun. That's not bad, not bad. Okay, so there's a little explosion in the chamber, right like that, okay? And out of the chamber comes the bullet, okay? Now what happens is that little explosion actually pushes back with a certain amount of force on the gun. And it also pushes, let's see, I wonder if I can get a different color in here. Let's say this is the bullet in here, okay? It also pushes with that exact same amount of force on the bullet, okay? The exact same force. I know it doesn't seem that way. You know, well, why does the bullet go really, really fast and the gun go really, really slow? That's because the gun has a lot more mass, a ton more mass than a bullet, okay? But they still get the same force, okay? Just like if you pushed on both sides on somebody who's really, really heavy and somebody who's really, really light, and you push just as hard on both sides, the person that's really, really heavy isn't going to move as much as that person that's really, really light, okay? One last example you might know of is if you have a rocket, okay? I'm really not good at drawing rockets, okay? So I'm just going to draw the force diagram for the rocket. What ends up happening is you have explosions going in the rocket. It actually pushes air out, exhaust gases down through the bottom. And that explosion, that pushing down of stuff, actually causes the rest of the rocket to move up, okay? And the thing is, you got to have a lot of gases down here to be pushed down in order to create the amount of lift up in order to actually get this thing into space. It's really quite amazing. That's why you'll see that whenever you see a space, or whenever you used to see a space shuttle go up, you would see these huge tanks on the side, this huge tank in the middle. That's pretty much all fuel, because you need a ton of fuel to get that big, heavy, multi-ton shuttle up into space. And that's kind of why we have a limit as far as what we can put up into space, because the heavier and heavier it is, the more and more fuel it needs, and the fuel itself weighs a whole bunch. So it just becomes this big problem. It's a lot easier to send really small stuff like satellites into space than other things. Anyway, I think I'm rambling a bit now, but that's Newton's third law. Just remember, if object A exerts a force on object B, B exerts a force on object A, and those forces are going to be the same type. They're going to be equal in size and opposite in direction. I hope that makes sense. If you have questions, please ask me in class, and I'll see you then.